So the question is, a 30-kilogram child moving at 4.0 meters per second jumps onto a 50-kilogram sled that is initially at rest on a long, frictionless, horizontal sheet of ice. Determine the speed of the child sled system after the child jumps onto the sled. First of all, we notice that it says frictionless. Frictionless means that energy and momentum are conserved because there's no external forces acting upon the system. And since it's asking for speed, in this case velocity, we can use the conservation of momentum to solve for the speed of the child sled system. So we use Pi is equal to Pf, which is the conservation of momentum. We know that momentum is equal to mass times velocity, and we know that the child has the initial momentum because the sled has zero velocity at the beginning. So it's 30 kilograms times the 4 meters per second, and so this is the momentum of the child equals the 30 kilograms of the child plus the 50 kilograms from the sled, all times Vf. And we're trying to solve for Vf, so we isolate Vf on one side, and Vf is equivalent to 120 over 80, and Vf is equal to 1.5 meters per second. So that's the first part of the question. The second part of the question asks us to determine the kinetic energy of the child sled system after the child jumps onto the sled. So in this case, we're going to use the equation for kinetic energy, which is 1 over 2 mv squared, and we know that the mass of the child is 30 kilograms. We know the mass of the sled is 50 kilograms, and we also know that we know Vf from the previous problem that we just solved is 1.5 meters per second. So we just plug these values into the equation. So Ke equals 1 over 2 times the mass, in this case 30 plus 50 times 1.5 squared, and that should give you 90 joules. So that's the second part of the question done. The third part of the question, they add this new part now where the child jumps off the sled, and now we have to determine the speed of the sled after the child jumps off the sled. So for this part, we're going to use the conservation of momentum again, and we know again that Pi equals Pf, and in this case, the initial momentum is the momentum of the child. As we calculated before, Pi is equal to the 30 kilograms from the child times the 4 meters per second, so it's equal to 120 kg meters per second, and we have to compute Pf, and Pf in this case is equivalent to the final momentum of the child and the sled, because now the child jumped off, so it's separate, but they're still part of the same system. So the mass of the sled individually is 50 times Vf, which is what we're solving for. We'll call it Vf in this case, plus the 30 kg from the child times 0 because the child jumped off, and we're assuming the child is stationary now, and so it's 0 meters per second for the child. So we completely ignore the part about the child in this equation because 0 meters per second, so we're only calculating for the velocity of the sled, and so we plug in 120 equals 50 Vf, and in this case Vf is equivalent to 120 over 50 equals 2.4 meters per second. And so now we go on to part D. Part D asks us to determine the kinetic energy of the child sled system when the child is at rest on the ice. So in order to determine the kinetic energy of the entire system, we have to take in Ke, and we'll call it net, so the net kinetic energy is equal to the kinetic energy of the child plus the kinetic energy of the sled. And so in this case, again, we know that the kinetic energy of the child is 0, like the last one, the velocity is equal to 0, so I'm just going to ignore the kinetic energy of the child. So Ke net is going to be equal to Ke sled, and Ke is equal to 1/2 mv squared, and we're just going to plug in the values here, 1/2 times 50, which is the 50 kilogram value we got from the last part, the previous question, and that's going to give us the Ke, the net Ke, kinetic energy, is equivalent to 144 joules. And so this leads us to, I believe, the final part of the problem.
So for part E, they want us to compare the kinetic energies that were determined in part B and part D, and then they want us to see whether or not there was a change in kinetic energy and determine where that change came from, if there was a change. And so for part B, when the child jumped onto the sled, we got that the kinetic energy was 90 joules, and so afterwards, when the child left the sled, jumped off the sled, we got that there was 144 joules of energy, which means that there was an increase in energy from when the child jumped onto the sled to the point where the child jumped off the sled. And so we have to attribute this increase in energy to essentially an inelastic collision, because the child internally pushed off the sled, and so this is an internal change within the system that changes the total energy, although the conservation of energy applies. In this case, since the child internally pushed off the sled, there is a change in energy. Thus, we see that there is greater energy for part D, where after the child pushes off the sled, the child jumps out, and so as a result, we attribute this change to the inelastic collision between the child and the sled.